All right, let's talk about the preparation of alcohols and reviewing chapter 8. So this is when you started off with an alkene, understanding when you start with an alkene, you're dealing with two major carbons. I'm drawing them in different colors just because I want to use my markers, okay? Great. So if we pretend as if this double bond isn't there, we would say that this picture looks like this. And if I ask you to assign that these carbons, the top one that was blue would be tertiary, and the bottom one that was in pink would be secondary. That may play to be helpful later on. So now let's go through and talk about each one of these reactions. Starting off with the addition of water. We have two ways to add water. Currently, there's technically three, but right now these are the main ones that you would need to know, and I could go over the other one off to the side shortly. This one is called hydroboration. Hydroboration follows anti-Markovnikov's rule, which means it prefers to go to the least stable side. So what I'm adding for the both of these is water. So I'm thinking about where my largest group is going to go. Well, technically both of them, but at times you tend to focus on what you're looking at, the biggest electronegative group. So here, I expect my OH to go to the bottom, and that's if your instructor doesn't want stereochemistry. Please remember this reaction follows syn addition, which means this hydrogen and the OH should be on the same side. So if you didn't draw it in the plane like this and they ask you to put stereochemistry in, you would expect this OH and the hydrogen that's there to be cis, but then your stereochemistry for your group changes. So sometimes when you see this, people are like, Kessie, that's not syn addition. Remember, you're comparing the hydrogen and the OH that's there. That is syn addition. So that's the little trick for this one. You're still adding water with this group. This was oxymercuration, demercuration. If you forget the THF, that's fine, but everything else is required. So please be sure now that this follows Markovnikov's rule, and it is going to be anti-addition, which means at the end of the problem, I'm expecting the OH and the hydrogen to be trans. But again, sometimes the instructors will let you get away with just placing it at the more stable location. If not, and they ask for stereochemistry, which I would just ask your instructor, here it's anti, so that means I know that whatever wedge or dash I put my OH in, the hydrogen would be opposite. I'm only focusing where the double bond used to be, so you shouldn't be adding these things in crazy locations. And then my isopropyl group would now be forced to have stereochemistry, so it would look like this. Then you have your, in the book, they may have called this hydroxylation or creation of a cis diol. When you're creating cis diols, please remember you're allowed to use the OS, O4. Come up with some funny things to remember them. I did in Orgo 1 when I taught my students, I would come up with funny things like Ozzy Osbourne has 4 kids that he took to the pyramids and they drank salty water. Hey, it works. There's a freebie for you. Another one that you can memorize would be KMNO4 over basic conditions. This is me also going over Orgo 1. It makes a difference, but both of these do the exact same thing. You can use either or. And where the location of where the double bond used to be, you would create your cis diols. I think I just like doing wedges a lot because I like to color in, but they could have also been both the dashes, and then the isopropyl group would have gone to the back. As you can see, I put the isopropyl all the time to the back because I have a need to color things in. When you're doing from an alkene using MCPVA, this was creation of a cyclic ether or an epoxide. Epoxides are always cis notation, so it's normally written as small m CPBA, which is metachloroperoxybenzoic acid, which is this structure right here. If they do not write this out, they could draw this, or they can write RCO3H. The CO3H part is the peroxybenzoic acid part. Memorize this as a unit, it's necessary, and remember, wherever your double bond is where the reaction happens. I'm gonna try my best to force myself to put it in dash. So that's an oxygen, like in a triangle, and then you would have your isopropyl group as a wedge. Now again, come up with some cute things to remember this. I think I had a student who told me they love food just like I did, so I definitely approved of this one. I went in a McChicken with a peanut butter sandwich and an apple because I'm greedy. And it works, so whatever it takes to remember it. Then whenever you open an epoxide, you will learn about this when we get into the epoxide chapter, so understand it now. You have different types of acid you can open up an epoxide with. Right now we're using the generic one being, and I call it generic because these are the only ones that will lead you to get you a trans diol. And I lied, it's not the only one. These are the acidic ways in order to get the trans diol. There's a basic way to get a trans diol, and I can also open it up with an inorganic acid being HX, like HBr, HCl, and I can create a different structure, but we're currently talking about diols. But everything I just said is still coming up in the near future. Then when we open an epoxide, once we go through later on for a mechanism in that particular chapter, you will learn that the acid tends to want to attack the more stable side of the ring when opening up, which means I would keep the lowered stability one as a dash, change the other one where it's being attacked to a wedge in this case, which should be opposite of whatever your epoxide look like, and then my other group would have been forced to the back. All of these reactions came from the alkene chapter, so please kindly review and let me know if you have any questions.